When things dissolve, they're actually dissolving in an equilibrium. Some of the things are dissolving while some are undissolving. This is happening at such a molecular level that we don't see it. In order to do the solubility product constant, or KSP expressions for these, we first have to write out the chemical equation for the dissolving of a given salt. Because these are all assumed to be salts, they are solids until they are put in solution, in which case they dissolve into ions, which are then aqueous in the solution. So as we look at some of the problems on our worksheet, in order to do the solubility product expressions, first we're going to write the dissolution equation. So number one, first we have to know the formula for strontium sulfate, which is SrSO4. Again, this is assumed to be a solid salt that we put in water. Because it's at equilibrium, we do the double arrows, and it's going to dissolve into strontium ions, which are dissolved in water, so we put AQ. And sulfate ions, charge of -2 or 2-. And at this time, you can use that interchangeable. Either way means the same thing, charge of -2. Now to write the KSP expression, we do the same thing we did for any equilibrium constant expressions. We do the concentration of the products. In this case, they are ions, raised to the power of their coefficients. And in this case, these coefficients are both 1. And because the product is a solid, we don't have a denominator. So this is the KSP expression for strontium sulfate. Number 2, where we have MgCl2, magnesium chloride. It's going to break into magnesium ions. And in this case, we're going to have 2 chloride ions. Now notice this is not Cl2 because this is an ion, not an element. So this KSP expression is going to be the concentration of Mg plus 2 times the concentration of chloride ions. And because we have this 2 here, we're going to square it. So this is our KSP expression. Moving on to part 3, we can use the KSP expression that we completed in part 1 to find the equilibrium concentration of dissolved ions. Now the first 3 of these are more difficult, and we're not going to worry about those in this class, so you can cross off the first 3. Let's do a sample of one of these that's not on this sheet. Let's consider the salt silver iodide. This is going to dissolve into silver ions and iodide ions. Again, we don't have I2 here because it's not an element, it is an ion. If we were given that the KSP for this salt is 1.5 times 10 to the minus 16th, and we know that the KSP expression for this is the concentration of silver ions times the concentration of iodide ions, we can actually solve for the concentration of the silver ions and the iodide ions in a perfectly saturated solution. If you have 1 mole of silver iodide, it's going to break into 1 mole of silver ions and 1 mole of iodide ions. Also, if you were to have 3 moles, it would turn into 3 moles of silver ions and 3 moles of iodide ions. So you see that this is a 1-to-1-to-1 ratio. So the concentration of silver iodide is going to equal the concentration of silver ions, which is also going to equal the concentration of iodide ions. So if we call this concentration X, the concentration for the iodide ions is also going to be X. So our KSP is X squared. So to solve for the concentration of ions at equilibrium, we can now say 1.5 times 10 to the minus 16 equals X squared. Solving for X by taking the square root of both sides. We can say now that the concentration of silver ions equals the concentration of iodide ions. Taking for the square root of x, and we get the concentration to be 1.2 times 10 to the minus 8th moles per liter. Remember, concentration in this case is molarity, so that's the number of moles for every liter. Notice above, if we look at the KSP expressions for each of these, the smaller the KSP expression, the less is dissolved. Smaller KSP, less can dissolve before it becomes saturated. All of these salts are actually not very soluble. These are very slightly soluble salts. The bigger the KSP number, the more will dissolve in solution. Given this information, you can solve numbers 4 and 5. The concentration of lead ions equals the concentration of sulfide ions. You'll write out your KSP expression. That will be x squared. So you'll take the square root of KSP in order to find the concentration of lead ions and the concentration of sulfide ions. The same thing will be done for calcium carbonate. Now going to our final section on this worksheet. In order to find if a solution is at equilibrium or not, we're going to use a QSP value in the same way we did Q values for regular KEQ equations. This is a type of KEQ equation, so we can use a QSP. Keep in mind that if the QSP is less than the KSP, then more can dissolve. It is an unsaturated solution. And if you were to lower the temperature, it will not precipitate out. The solid will not form a precipitate. If the QSP equals KSP, this is a perfectly saturated solution. You have exactly as much solute dissolved. At the temperature that it's showing you that was cooled, so it will not precipitate out. At the higher temperature, it was unsaturated. When you cool it to the temperature given to you with the KSP, it is now perfectly saturated. If QSP is greater than KSP, you have too much salt that dissolved at a higher temperature. As you cool it, it's now a supersaturated solution, so as you cool, it will precipitate out. So what we have to do is we have to do the math problems with QSP, compare the QSP to the given KSP to decide if it will precipitate or not. In order to do each of these problems, the first thing we're going to do is we're going to write the dissolution equation. So we have zinc hydroxide, ZnOH2. This is a solid. It is dissolving to form zinc ions and 2 hydroxide ions per zinc ion. So our QSP expression, same thing as KSP, but we don't know if it's at equilibrium, is going to be the concentration of zinc times the concentration of OH minus ions squared. Now to solve for the concentration, we're going to have to look at what's given to us. And we know that we start with 0.001 moles of zinc hydroxide in 50 liters of water. So we're going to have to solve for the molarity. So the concentration of zinc ions, first let's do the concentration of our full salt in the water. When we initially put this in the water, we have 0.0001 moles of zinc hydroxide per 50 liters of water. And in the case of these, I'd like you to go ahead and add an extra 0 here so that we can keep the significant digits the same as we get in the QSP value above. So once we calculate the concentration, we find that it is 2.0 times 10 to the negative 6 molar solution. So we've got 2 times 10 to the negative 6 moles of zinc hydroxide. So for every 2.0 times 10 to the negative 6 moles of zinc hydroxide, we're going to get 1 mole of zinc ions, because this is a 1:1 ratio of zinc. However, we're going to get 2 ions of the hydroxide for every 1 formula unit of the salt. 1 unit of salt is going to give us 2 units of hydroxide ions. So the concentration of OH minus is going to be 2 times the concentration of the salt. So plugging this into our QSP expression, we're going to get the concentration of zinc ions. This is -6, I'm sorry. And the concentration of the OH minus ions, which is now 4.0 times 10 to the negative 6, and we have to square it. Because this is squared above, we're going to square this here. We're going to put this in our calculator and see what we get for the QSP, and once you put it in, you will find that the QSP is 3.2 times 10 to the minus 17. This is QSP. You'll notice the KSP that they give us in this equation. In the problem, they're going to give you the KSP, and the KSP is 4.5 times 10 to the negative 17th. So you notice that the KSP is a bigger number than the QSP, which means that you could dissolve more in here. Again, if we look above, in this case, the QSP is less than KSP, so no precipitate will occur. Another example is you're trying to determine the concentrations. If we were to look at barium phosphate, in order to determine the concentrations of this, for every 1 mole of barium phosphate, you're going to get 3 moles of barium ions and 2 moles of phosphate ions. So to determine the molarity of the barium ions, you take the initial concentration of your initial solution and multiply it by 3. So 3 times the initial concentration of your salt as you initially put it in the water. To find out the concentration, I'm sorry, this is plus 2. To determine the concentration of your phosphate ions, it's going to be 2 times the initial concentration. To review the steps to solve the ion products, to see if a precipitate will form, that's in part 4 of this homework. Step 1, you're going to write the dissolution equation. Step 2, you're going to write your QSP expression, which is the same as the KSP expression. We just don't know if it's equilibrium. Number 3, we're going to determine the concentration of ions of each ion. Step 4, we're going to solve QSP. And step 5, we're going to compare the QSP to KSP to determine if the precipitate will form.